Okay, let's go ahead and get started. What questions do you have? What do you want to see worked out? We will start at the beginning with Chapter 4. So what do you want to see from Chapter 4?
Question 3.
Problem number 3 from Chapter 4. This is the problem relating to the guy that's trying to shoot the bird. Right? Literally shoot the, we're not doing this, we're shooting a bird. Okay? So, what do they tell us in the problem? Once again, let me, can I use your book?
Yeah.
Yeah. I will just use your book and read the questions. Chapter 4, problem number 3. The fastest bird is the spine-tailed swift, which reaches speeds of 171 kilometers per hour. Suppose that you wish to shoot such a bird with a .22 caliber rifle because you're a jackass, and that the gun fires a bullet with a speed of 366 meters per second. If you fire at the instant when the bird is 30 meters directly overhead, how many meters ahead of the bird must you aim the rifle? Ignore gravity in this problem. All right, so let's write down everything we're given. We're given that the velocity of the bird is 171 kilometers per hour. Right away, I see kilometers per hour and I panic. Why do I panic?
Meters per second.
It's not SI, I wanted it in SI system. So I'm going to convert that into the SI units. 1 kilometer is 1,000 meters. And 1 hour is 3,600 seconds. So my hours cancel, kilometers cancel, and the velocity of the bird is now 47.5 meters per second. I'm also given that the velocity of the bullet is equal to 366 meters per second. And I'm given that there's some vertical height the bird is. It is 30 meters directly overhead. So those are all the numbers that I'm given, and I'm also told to ignore gravity, right? All right. So I don't need to worry about G, that's nice. What I need to do, I need to draw a picture. Here I am, standing here, aiming my gun. Wow, I've got a long arm and a little gun. And a very freaky looking bird. There's my bird. Okay, and that bird is directly over my gun. What's the distance between my gun and the bird?
30 meters.
30 meters. So that's the vertical distance between the two of us. If I aim my gun directly up, will I hit the bird?
No.
No, because the bird's got some velocity carrying it forward, right? So I need to aim at where the bird's going to be. So I need to figure out what that is. I need to figure out where the bird's going to be. Bird's going to be somewhere over here. So I need to aim somewhere over there, anticipating where the bird will be. Yeah? Okay? We'll call this some change in x.
So is that what we're looking for?
We're looking for change in x. Okay, what else do I know?
Velocity of the bullet.
Velocity of the bullet. So that's going to be this hypotenuse here. If I were to draw this in, it's kind of a right triangle. Velocity of my bullet is equal to 366 meters per second. Okay, do I know anything else? Velocity of the bird? How would I draw that in here? Yep, going towards the point where it's going to run into the bullet. Poor bird. So let me draw the velocity of the bird in here. And I'm going to do the velocity of the bullet in red. Okay, so I know the velocity of the bird, I know the velocity of the bullet, I know this 30 meters, I know I'm looking for some delta x. When I look at this, I see a right triangle in here. Can you see the right triangle? Yes. Okay. I know the velocity of the bullet. So what side of the triangle is that? It's the hypotenuse. And I know the velocity of the bird, this part over here. That's one of the sides. We'll call that the opposite, and we'll identify this angle right here. Theta. So I can find theta, can't I?
Yes.
Theta is going to be the inverse sine of the velocity of the bird, which is 47.5, over the hypotenuse, 366. So I did my right triangle trigonometry we've been doing seemingly forever. So what's this angle if I solve this out?
7.5.
7.5 degrees. Okay, so that's the angle that I aim at. Is that actually giving me what I want?
No.
What do I want?
Change in x.
I want change in x. If I know theta is equal to 7.5, how can I get change in x? Do I know any other sides of this triangle? Do I know what the hypotenuse is in terms of a distance?
No.
I'm trying to find a distance. Delta x is a distance. So I don't know the hypotenuse. I'm looking for this. How about the adjacent side? The adjacent side. Do I know that?
Yeah.
How big is that? 30 meters. So I can write down another relationship. Tangent of theta is the opposite side, that delta x, divided by 30 meters. So 30 meters times my tangent of 7.5 is going to give delta x. And you will find that delta x is equal to, on a very, very messy slide, 3.93 meters. So that's how far ahead you have to lead the bird. Okay? Any questions on that? Number 3 from chapter 4. We'll do chapter 4, number 87. At the entrance of Ambrose Channel at New York Harbor, the tidal current at one time of the day has a velocity of 4.2 kilometers per hour in a direction 20 degrees south of east. Consider a ship in this current. Suppose that the ship has a speed of 16 kilometers per hour relative to the water. If the helmsman keeps the bow of the ship aimed due north, what will the actual velocity, magnitude, and direction of the ship relative to the ground be? To give us a bunch of information, it's going to be a relative velocity problem, and I need to figure out what's going on. So first I'm going to draw a nice big picture. What direction is the current going?
20 degrees south of east.
20 degrees south of east. So I'm going to draw some vectors that represent that current. Okay. And it's going to be moving 20 degrees south of east. So that angle right there is going to be 20 degrees. And that's where my water is actually going. Yeah? And I have a ship. My ship, I'm going to aim. What direction am I going to aim my ship?
North.
Aim my ship directly north. Due north. So that's going to be V of my ship. And blue is V of my water. Then I also know one more thing. They give us... Do they give us the velocity of that ship?
16 kilometers an hour.
Velocity of ship is 16 kilometers per hour.
And the current's 4.2.
And current is 4.2. So that's the water relative to the ground. Do I need to change this into SI system?
Yes.
You can. Turns out you don't actually need to change this one. You're just finding velocities, so your velocities will be in kilometers per hour. It's up to you. You can put it into SI. I am not going to. Okay. What you want to do for these problems, relative velocity problems, is separate into the X and Y directions. Same as with any problem that we've been doing. So you'll have this picture on your minds and in front of you. Well, we're going to move to a different... What's the velocity of the ship in the X direction?
There's none. 0.
0. What's the velocity of the ship in the Y direction?
16.
16 kilometers per hour. What's the velocity of the water in the X direction? Let's draw a quick little reminder of what the water looks like. The water is going like this. 20 degrees south of east. So what's the water velocity in the X direction?
4.5 sine of 20.
I think they said 4.2?
Oh, 2, sorry.
4.2 kilometers per hour. And is that times the cosine or the sine?
Sine. Oh, cosine, sorry.
So that's the adjacent side to my angle. So that's going to be cosine. 4.2 times the cosine of 20 degrees. So I have V water in the X direction. When you multiply this out, you'll get 3.9 kilometers per hour. How about the velocity of the water in the Y direction? .2 sine of 20. Got one question for you. That water looks like it's going south, right? It's going down.
Negative.
So it's going the opposite direction to where the ship's going, isn't it? So it should have a different sign, shouldn't it? Yeah, if I draw out these vectors, I have one going to the right, and I have one going down for the water. So that down one should be negative. So we want to put in a negative 4.2 sine of 20. V water in the Y direction. Also call it V watery. Okay. Multiply this out and you'll find negative 1.4 kilometers per hour. So let's keep all of these things in mind. We need to know velocities in the X and Y directions. And we're going to combine these velocities to get what velocity the boat actually goes at. So if I want the velocity of the ship relative to the ground, ship to ground, in the X direction, then I need to take the velocity of the ship in the X direction relative to the water, and I need to add the velocity of the water in the x direction relative to the ground. And that'll give me the velocity relative to the ground of the ship. How fast was my ship going in the x direction? 0. Big fat goose egg. How fast was my ship going in the y direction? Or in the, how fast was my water going in the x direction? 3.9 kilometers per hour. So my velocity of my ship relative to the ground in the x direction is 3.9 kilometers per hour. How about velocity of the ship relative to the ground in the y direction? It's going to be v shippy minus v watery. What's the velocity of the ship in the y direction? 16 kilometers per hour. What's the velocity of the water in the y direction? Okay. And that's where I should point something out. Velocity, relative velocities, you add your two velocities together. So up top, velocity of ship relative to ground, v ship x plus v water x. Add them together, get my result. I come to the y, v ship to ground in the y direction, v ship y minus v water y. So I plugged in that negative from the beginning because I knew they were going in opposite directions. Okay, so I don't need to plug in a negative 1.4 for the v water because I put that in.
Is it always going to be negative, or is it just relative to this problem?
Just for this problem. If your velocities are in opposite directions, they'll be negatives. Okay. So I plug these numbers in, and I get velocity of the ship relative to the ground of 14.6 kilometers per hour. So the boat gets slowed down a little bit because the current's pulling it down, slowing it a little. So this is all making sense physically. Let's drop a picture of what the boat looks like. Here's my coordinate axes. Here's where my water's going. My boat. What was Vx? Somebody have Vx for me? 3.9 kilometers per hour. What was Vy? Total Vy? 14.6. Yeah. So I can draw a vector that represents this. I can go over 3.9-ish. And I can go up 14.6-ish. And that guy right there is where my boat is going. That's my total velocity of my boat. It's the vector addition of Vx and Vy. That's what my picture looks like for this. So I have an angle in there. How can I find what V is? If I know Vx and I know Vy. V equals the square root of Vx squared plus Vy squared. Where did we get that from? Pythagorean theorem. How long have we been doing Pythagorean theorem in here? Since the first day. Forever. Plug in your numbers, find that V is equal to 15.1 kilometers per hour. That is the magnitude of the velocity of this boat. Now I want to know the direction. I want to know that angle. How can I find the angle? pick a trig function. You know every side of that triangle. I picked tangent. So tangent of theta is opposite over adjacent. What's the opposite side? Vy. What's the adjacent side? Vx. So you can plug in your numbers and you'll find a theta that's equal to 15 degrees. What direction is that 15 degrees? Remember, we had north, we had south, we had east, we had west. I'm going 15 degrees north of east. East, not west. So I start out going east, and then I'm going north of that for my angle to get my vector. That would be problem 87A. Moving on to chapter 5, we're going to do number 35. So in this problem, we have a man that weighs 750 newtons on the Earth. The surface gravities of Mars and Jupiter are 0.38 g and 2.53 g respectively. What is the mass of the man on each of these planets, and what is his weight on each planet? All right. So we're given right away. What is this man's weight? Think of us.
750.
Fg is 750 newtons. I can use that to get this man's mass. I want to know what his actual mass is. How much mass is inside of his body? How can I do that? Fg is mg. Fg is mg. Solve this for m, right? So divide both sides by g. G's cancel on the right. So mass is Fg over g. So we have 750 newtons divided by 9.8 meters per second squared. And I get that the mass of this man is 76.5 kilograms. So that's going to be his mass on every single planet, right? Because mass doesn't change. So that is his mass, no matter where you send it. How do we find his weight? What is weight? Weight is mass times acceleration. Fg, this is weight. Fg is mg. Yeah? Okay, so if I want to know his weight on Mars, his Fg is going to be equal to his mass. Mass doesn't change, right? Times the acceleration due to gravity on Mars. So I can do the mass. And what is g on Mars? They give it to you.
38.38.
0.38 g. Oh, 0.38 g. Do you know your mass? What is your mass? 76.5. Do you know g? What's g?
10.8.
G is 9.8. So you do 76.5 times 0.38 times 9.8 and get your final answer for weight on Mars. Fg on Mars is 285 newtons. Does that make sense?
Why couldn't G just be 0.38?
Because it's 0.38 g. So that means it's 0.38 times g.
I see.
Times gravity.
I thought it was saying like 0.38.
The gravity,
That's the gravity.
Yeah, the gravity on Mars is about a third of what it is on Earth. Because the planet's smaller. Yeah, so for Jupiter, what would you do?
Same thing.
Same thing? Is it the same gravity?
No, it's 2.53.
It's 2.53 G. Okay. That should be problem number 35. So do chapter 5, problem number 51. In this problem, in order to pull an automobile out of the mud in which it is stuck, the driver stretches a rope tautly from the end of the automobile to a stout tree. Not just any tree, it has to be stout. He then pushes sideways against the rope at the midpoint. See the figure below. When he pushes with a force of 900 newtons, the angle between the two halves of the rope on his right and his left is 170 degrees. What is the tension in the rope under these conditions? So he's going to try to use tension to pull this car out of the mud. Think it's going to work for him? I don't think so. I think he's a moron. That's why you have AAA. So we have a picture that looks kind of like this. We have two ropes. We have this guy that's pushing in the middle of the ropes, right? He's applying a force upwards. Force of that push. How big is that push?
900.
900 newtons. It's a lot of cookies. Fig Newtons. It's late. This is past my bedtime. So what is this angle that we have between these two ropes? 170 degrees. So that whole angle is 170 degrees. That's pretty much all we're given, isn't it? Yeah. What kind of jackass writes a problem like this? Barely gave us anything. So what do we do when we have things working at angles? Break into X and Y. Try to find right triangles. Okay? Lots of different right triangles we can find in here. I can find one that's going down like this. And then kind of going over. I can find another right triangle that's going down. Going the opposite direction. Yeah, I see those two right triangles. I need to find some angles. I need to find some angles. Can I find the top angle in that right triangle?
Yes.
How?
It's half of 170.
Half of 170. What's half of 170?
85.
85. So each one of these angles is 85 degrees. Yay. I'm going to label these kinds of things. I'm going to label this tension. I'm going to label it in red. And that's kind of on the left side, right? So I'm going to call that T left. And the other tension, you're doing that in blue, I'm going to call that T right. So that means I can label these components, can't I? I can label a T left X. And T left Y. T lefty. Sounds like a bad mobster. But not as bad as his cop brother T righty. Lefty and righty. Man, I do need to get some sleep. And then T right X. So all I've done is separated this into the X components and Y components. Right? Now I can identify what things are going on in each direction. Let's do the Y direction first. Let's do the sum of the forces that I have acting in the Y direction. What forces do I have acting up? Are there any forces going up? F push. Any forces acting down? T lefty, and T righty. This is going to be equal to the mass times the acceleration in the y direction. What is the mass times the acceleration in the y direction?
0.
And why is it 0?
Because there's nothing that's moving.
Because nothing's moving. He's not having much success with his little clever scheme to get his car out of the mud. Okay, so this is equal to 0. Question.
Why wouldn't T left and T right be plus? 'Cause they're going in the same direction.
So, F push is going up.
Right.
So that's positive. Yeah? T lefty is going down. So I said that's negative.
Okay.
Yeah.
I
And then
see.
T right
It's going down.
is going down, so that's negative. So they are going the same direction. They just happen to both be negatives.
Okay.
Yes?
So like, aren't they both the same? Because they're like,
Yeah. It's symmetric.
but you still have two different triangles.
Yeah. Yeah. Just the size of those triangles is symmetric. It's the same. So you could do 2 times T lefty or 2 times T righty.
But like, why would you do that? Because it's like, it's just one, it's just like going down, right? Not going down, but like the tension is like it's the same thing, right? Isn't it? Why do you have like two?
So I broke it into 2 triangles because of the x direction. So in the y direction, it's pretty clear. You could say one tension that's going down, but then that gets confusing for the x direction. You need the x direction too. So we'll see that in a second. Okay. Because we need to figure out what T left x and T right x are. Before we do that, let's find out what Ty left and Ty right are. So let's find them in terms of T left and in terms of T right. That's the hypotenuse of this triangle. What's my angle? My angle is 85. So which side of the triangle is the y component? It's the adjacent side. So what trig function do I use? Cosine. So T left in the y direction is going to be T left times the cosine of our angle, which is 85. And we can use the same reasoning. T right in the y direction is T right times the cosine of 85. And T left and T right, they're equal, right? Yeah, so I'm just going to call them T. So our sum of forces in the y direction is the F pull, or F push I think we called it, which is going up, minus 2 times the tensions that we have in the y direction, which we just figured out. F push minus 2 times T cosine of 85. And what was that equal? That was equal to 0? Yeah. Okay. So I know F push is equal to 2 times T times cosine of 85. I guess we don't need the x direction at all. I know what F push is, don't I? What's F push? 900 newtons. equals 2 times t times cosine of 85. I can solve that for t, can't I? T is the only thing I don't know. I can find that t is 5.16 times 10 to the third newtons. (5,160 newtons). So that's a lot of force. I think his rope would break. He'd need a steel cable. I think the car would break. The bumper would pop off. If he's pushing with that much force, I think the cable would dig into his hand and like chop his hand off. I don't know. Okay, so that is problem number 51. Right, we're going to do chapter 5. Problem number 47. We have two heavy boxes of masses 20 kilograms and 30 kilograms that are sitting on a smooth, frictionless surface. The boxes are in contact, and a horizontal force of 60 newtons pushes horizontally against the smaller box. What is the acceleration of the two boxes? What is the force that the smaller box exerts on the larger box? And what is the force that the larger box exerts on the smaller box? Okay. Let's draw that picture. What does this whole thing look like? They give us a picture in the book that looks something like this. We have our box. We have mass 1 and mass 2. Mass 1 is the smaller box, it's 20 kilograms. Mass 2 is the larger box, it's 30 kilograms. And I'm pushing with a force that's equal to 60 newtons. Okay, I want to find the net acceleration of these two boxes, right? That's what they ask us for. I have the sum of the forces acting. Whatever those forces are is going to be equal to the total mass times the acceleration of both boxes combined. I can break this up so that the sum of the forces acting is equal to the total mass, which is going to be mass 1 plus mass 2 times the acceleration. And I can solve this for acceleration to find acceleration is equal to the sum of the forces that are acting divided by mass 1 plus mass 2. Is there any friction in the problem?
No.
Nope, they're on frictionless surface. What forces do you see that are acting on these two boxes?
Push.
I see F push. Any other forces? No? Don't need to worry about those.
Gravity.
All we care about are the total forces acting in the direction that we're accelerating. I'm accelerating in the x direction. Gravity's acting, but where does gravity act?
Y direction.
Acts y direction. Do we have to worry about it?
No.
No. We just care about the net force, which is going to be that 60 Newton push, divided by the total masses that we have. 20 kilograms for mass 1 plus 30 kilograms for mass 2. So the acceleration that both these boxes experience at the same time is 1.2 meters per second squared. So that's the total stuff that we have acting on the two-box system. We don't have to break it up into different components, into different pieces. There are more forces at play here, but all we care about for the first part is the total force on everything, which is that 60 newtons. Now we can break them up. Let's break up the boxes. Let's do box number 1. Box number 1, this one right here. What forces are acting on that box? I've got F push coming in from the right-hand side, correct? But then I also have another force acting on it, right? It's going to be squeezed up against that second box. So that second box is going to push on the first box, isn't it? So what direction does the force of box 2 on box 1 go? Goes the other way, goes opposite. Force of box 2 on box 1. And all I care about are the forces that are acting on that first box. Any other forces acting on the first box? Don't care about gravity? We only care about the direction we're going. Okay? So let's write down the sum of forces for that guy. For box 1. Sum of forces is equal to what's pushing it to the right? F push. What's resisting that push? F of box 2 on 1. That's going to be equal to the mass of box 1 times the acceleration. How fast was this accelerating? Do we know how fast it's accelerating?
1.2.
Yeah, so we know A. Do we know how big the mass is? Mass 1? Yeah. Do we know F push?
Yes.
Yeah, so the only thing we don't know is F21. We can solve this for F21 and find the force that box 2 on box 1. So let's solve it. F of 2 on 1 is going to be equal to F push minus M1 times A. Plug in your numbers. F of 2 on 1 is 60 newtons for F push minus 20 kilograms times my acceleration of 1.2 meters per second squared. So F of 2 on 1 is equal to 36 newtons. Any questions on that?
That would be the push going to the left.
That's the push going to the left that box 2 exerts on box 1. Okay. All right. So what do we do to find the force of box 1 on box 2? We could do some summing of forces, or we could use some physics. What does Newton's third law say? Every action has an equal and opposite reaction. So if box 2 is pushing on box 1 with a force of 36 newtons, box 1 is going to respond to that force. How big is box 1 going to respond to box 2 with? What force? Yep. F of 1 on 2 is going to be 36 newtons. So let's look at the signs here. Usually anything going to the left we consider to be negative. Yeah. So 2 on 1 would be negative, and 1 on 2 would be positive. Okay. That's problem number, 47. All right, let's do chapter 6, problem number 9. In this problem, we have a baseball player that's sprinting at 4.5 meters per second, and he begins to slide with his body flat on the ground when 2.8 meters from home base. The coefficient of friction between the player's uniform and the ground is 0.3. Does he make it home? And if so, what is his speed as he reaches home? Ooh. So we are told that we have some initial velocity for this runner, and that's going to be 4.5 meters per second. Change in x, it's going to be 2.8 meters, hopefully. Right? We say hopefully because they actually don't tell us that they reach that actual distance. Does he make it home? Does he make it 2.8 meters? The final. Some final velocity. Do we know what the final velocity is?
No.
Slide into home. What happens when you slide into home? As you're sliding along,
Slow down.
you slow down. Do you eventually stop? Yeah. So we can say his final velocity is going to be 0, and that's going to tell us where he is when he stops. Okay. So we're going to use that. Let's identify the forces that are acting on this guy. So here's the ground. Here's my dude. He's sliding head first. So it kind of looks like he just kind of fell down. But he slid. This distance, delta x. Head first, mind you. He's one of the lower paid players. What forces are acting on him? Friction. So what direction does friction go? Opposite to his motion, so back from where he came, from whence he came. Force of friction. What are the forces? Gravity. I know people are yelling in the hallway. That's anything to imagine being outside of class. What else? Normal force. Where does the normal force go? Upwards from gravity. When you're doing problems with friction, you'll always be finding the normal force. There'll always be some kind of normal force, because you need that to actually get friction. So if I do some of the forces that are acting on this guy in the x direction, some of the forces in the x direction. What forces do you have?
Friction.
Friction. What other forces?
That's it.
That's it. Force of friction equals, what's the force of friction? Mu times the normal force. So that's our x direction. Let's do sum of forces in the y direction. What force is acting up? Normal force. Gravity is acting down. Equals 0. He's not bouncing up and down as he's sliding into home plate. Hopefully. So we have the normal force is equal to Fg. What is Fg? Mg. So the normal force is equal to mg. So I can plug in the force of friction, which is mu times Fn. Force of friction is mu times m times g. Oh boy, how does this help me? Anytime I'm writing the sum of forces down for a sum of force equation, what is that always equal to? The very end.
0.
What's Newton's second law? Newton's second law.
Force equals ma. So
F equals ma. Sum of forces is always equal to mass times acceleration. Usually we end up with this wonderful little 0 acceleration. So in the y direction we had 0 acceleration. This guy that's sliding into home plate, does he have 0 acceleration? No, he's slowing down, right? He has some acceleration. So this force of friction equal mu Fn is also equal to mass times the guy's acceleration. So this is equal to mass times acceleration. What can I do to mass?
cancel it out.
I can cancel it out. I don't care what mass this guy is. He can be the fattest baseball player you have ever seen. And this will still work. And I can use all of this to find what A is. A is equal to mu times G. That's going to be the magnitude of his acceleration. Okay? A is equal to mu times G. What is mu? 0.3. And G is 9.8. So our acceleration is equal to 2.94 meters per second squared.
Where do you get the mean from?
It's given. Yeah. They tell us in the problem. Okay, so now I know this acceleration. I can use the acceleration and all the other information I have to find what the change in position is. I can use the equation 1/2 times Vf squared minus V naught squared equals A times change in x. So here, let's look at that. So if I shuffle this around, I can solve for A, or I can solve for delta x. Yeah, just divide both sides by A. Plug in your numbers. Delta x is 1/2. Vf squared is 0 minus V initial, which was 4.5. Meters per second squared, divided by your acceleration of 2.94. And you'll find a delta x equal to negative 3.43 meters. Okay. Negative because he ended up, his motion was actually opposite the direction the friction was. So the question they asked is, does the runner make it to home plate? Home plate was how far away? It was 2.8 meters. So does he make it at least 2.8 meters? Oh yeah, he's got plenty of room. So runner makes it. Part A, runner scores. Part B, we're asked to find what the speed is as he reaches home plate. So we know delta x now is going to be 2.8 meters. V initial is still the same speed he had, 4.5 meters per second. We know V final is what we're looking for. We know the acceleration is 2.94 meters per second squared. Is there an equation I can use? Pick a kinematic equation, and you will plug them all in to get V final is 1.94 meters per second. So we should be able to solve that on our own. Let's do Chapter 6, problem number 45. This problem we have solid materials that can act much like springs. Consider a steel cable with radius 2 centimeters and length 20 meters, which has a spring constant of 1.4 times 10 to the 7 newtons per meter. If a 1,500 kilogram elevator car is hung from this cable, how much does the cable stretch? So the cables inside the elevators, they're actually stretching. They act like springs. They can move a little bit, even though they're made of steel. So we want to know how much that's going to stretch when we hang the elevator car from it. They tell us the cable has a radius of 2.0 centimeters. They tell you that to confuse you. That piece of information is completely useless, much like all of physics. We have the length of this cable is 20 meters. They tell us it has a spring constant of 1.4 times 10 to the 7th newtons per meter. They tell us we're going to hang a mass of 1,500 kilograms from this cable. Here's my elevator car. And I've got this steel cable that's going to stretch. When I have something stretching, it experiences a force. What force do you get when you're stretching things? It's not just tension. This is stretching like a spring. So we're going to have a Hooke's law spring force. Yeah. So we're going to have a spring force that's acting up. We'll call it Fs. What other forces are going to act? The force of yaw. Force of gravity. Gravity is going to be acting down. And what's Fg? Mg. What's an equation for Fs? S is Kx. Negative.
Is it negative KX?
Yep. Should be a negative in there. Okay. Yeah. I can balance these forces. I know that the spring force, when this thing comes to rest, it's going to stretch a little bit, but it's going to stretch an amount that's determined by this force of gravity. So I know that the spring force magnitude is going to be equal to the gravitational force. The gravitational force is causing this thing to stretch. And I'm just worrying about magnitudes because they don't ask anything about directions between these forces. So the direction of the spring force, or magnitude of that, is K times X. Magnitude of Fg is Mg. You're looking for how much the cable stretches. What variable is that? It's going to be X, so solve this for X. X is Mg divided by K. Do we know the mass? No, because we're just doing magnitudes. Just the magnitude. That's what those little bars mean. Have you ever seen those little bars before? Yeah. So we got 1,500 kilograms times 9.8 meters per second squared divided by the spring constant of 1.4 times 10 to the 7 newtons over meters. And this cable stretches 1.1 times 10 to the negative 3 meters. So we'll do chapter 6, problem number 17. We have a girl that pulls a sled along a level dirt road by means of a rope attached to the front of the sled. See the figure below. The mass of the sled is 40 kilograms. The coefficient of kinetic friction is mu k equals 0.6, and the angle between the rope and the road is 30 degrees. What pull must the girl exert to move the sled at a constant velocity? So we're told mass of this sled equals 40 kilograms. Coefficient of kinetic friction is 0.6. Right, unitless. What's the acceleration? Did they give us acceleration?
No.
No? Yes, they did. Did they give us anything about velocity? What does it say about velocity?
Constant velocity.
Constant velocity. If velocity is constant, the velocity is not changing, right?
Right.
So if the velocity is not changing, acceleration is 0. No acceleration. Pretty boring sled. So let's draw a picture. And instead of the little girl pulling on the block, it's just a big block. I don't draw nice pictures. We have some forces acting on this sled. What forces are acting on the sled? Gravity. Where does gravity go? Gravity is going down. And that's going to be Fg. What other forces? Fn. The Fn force is going up. What other forces?
Friction.
Force of pull. It's going up at an angle. For pull. And friction. Where does friction go?
Opposite.
Opposite to pull. Hello. Hello. I see something acting at an angle. What is that angle? How big? 30 degrees. And anytime I see things acting at angles, I break it into components. So I'm going to have some F pull in the X direction. And I'm going to have some F pull in the Y direction. What do you call this diagram that we just drew?
Full body.
Free body diagram.
Free body.
Is this full body diagram? Full body. It's a shampoo commercial. Anybody remember those shampoo commercials? So we have the free body diagram. We have identified all the forces. Let's do the sum of forces equations for the X and Y directions. Let's do X direction first. Sum of forces in the X direction. What forces are pulling me over to the right? F pull X. And how big is F pull X in terms of F pull? What side of the triangle is it?
Adjacent.
Adjacent. So that means it's the
Cosine.
cosine. F pull times the cosine of 30. Anything else moving it in the positive X direction? Anything in the negative X direction?
Friction.
Yep. Minus the force of friction is the mass times the acceleration in the X direction. What's the acceleration in X?
0.
0. Okay, so now I know that F pull times the cosine of 30 is equal to the force of friction. There's an equation for the force of friction. What's that equation? Mu times the normal force. So I can do F pull times cosine of 30 is equal to mu times the normal force. And we're going to label this as a mu k. What does the k stand for?
Kinetic.
Kinetic. Because this problem is friction where things are moving. Okay? So now we know F pull is equal to mu k times the normal force divided by cosine of 30. All right, let's look at this. Do I know mu?
Yes.
Yes. Do I know cosine of 30? Yes. Do I know Fn? No. Oh, crap. Not yet. N.
Y direction.
Y direction. Let's turn pages and go to the Y direction. Sum of forces in the Y direction. What forces are acting up? Fn. Anything else acting up? Plus F pull Y. Anything else going up? No. Anything going down? Fg. And from Newton's second law, we know this is equal to the mass times the acceleration in the Y direction. What's the acceleration in the Y direction? Big fat 0. You can tell we're getting excited. We're getting close. Let's solve this for Fn. Fn is going to be equal to Fg minus F pull Y. So I'm just moving things to the other side. Fn is equal to Fg. What is Fg? Mg. F pull Y This was the opposite side.
Yes.
So that's going to be F pull times the sine. Yeah. So now I have this equation for Fn. I can take this equation and plug it into my F pull equation. In F pull, I had F pull equals mu times Fn over cosine of 30. So I can plunk that little normal force right into there. So let's plug and chug. You get F pull is equal to mu times, when I plug in my normal force, mg minus F pull times sine of 30 all divided by cosine of 30. Let's take a stock of what we know. Do I know what mu is? I know what mu is. Do I know what m is? Yeah. Do I know what g is? Yes. So there's only one thing I don't know, right? The only thing I don't know is F pull. So I can plug in my numbers and I can solve this. Do a little bit of algebra, and you would find that F pull is equal to 200 newtons. And I would suggest actually going home and trying to do this algebra to make sure you can solve this out.